Hello friends, I am Snehal and we are studying physics. Last time we started with the applications of the Gauss Law and today we are going to see some more applications. So let us see application number 3. It is the electric field due to uniformly charged solid sphere. So suppose this is our solid sphere and this positive charge Q is uniformly distributed all over the volume of the sphere. That is, this charge is there inside the body of the sphere and we wish to find out its electric field at distance r away from the center. Now we are going to use the Gauss law for it, and we know that in order to apply the Gauss law we need to draw a closed surface called Gaussian surface, and Gaussian surface is determined by the symmetry of the problem. In this problem, the symmetry is quite clear. It's the spherical symmetry. So it should be clear that we need to imagine a concentric sphere passing through this point P. So let us draw this spherical shell. Center of this spherical shell and center of the solid sphere, they coincide. Now it should be clear that the magnitude of electric field at each and every point of the sphere, this Gaussian surface, is same. It's because this point P is not different from any other point, let's say A or B, taken over this Gaussian surface. All those points are at the same distance away from the center. So electric field at point P should be just equal to, in magnitude, the electric field at point A or any other point on the surface. Now what about the direction? So again, if we think over, it should be clear that the direction of electric field would be radially outwards or inwards. And since this is positive charge, the direction of electric field at point P would be radially outwards. So now let us recall the Gauss law. And Gauss law says that the electric flux phi through any closed surface, so this is our closed surface or Gaussian surface, the electric flux through any closed surface is equal to charge enclosed, so Q suffix ANC is the charge enclosed, divided by epsilon naught. This is the Gauss law. Now we know that the electric flux phi is equal to surface integral of electric field over the Gaussian surface. So this is over Gaussian surface. Alright, so let's consider any small surface area ds bar. So because we want to find the electric field at point P, let's consider the surface area ds bar here. So this is ds bar. Now we know that the area vector has a direction perpendicular to plane of area. So the direction of ds bar would be like this. This is the magnitude. So this is ds bar. And electric field is also in the same direction. It's in this radial direction. So this is electric field. Now we can write phi is equal to, over this Gaussian surface, so Gaussian surface is, let's say, S, E bar dot ds bar, as we know, it is E multiplied by ds multiplied by cos of the angle between these two vectors, and over this entire surface, wherever we take this point P and the surface ds, the electric field and the surface area element, they will have the same direction. So angle between electric field and surface area vector is just 0. So since theta is 0 and cos 0 is 1, we have the integral over this closed surface E multiplied by ds only. And we just argued that the electric field will have same magnitude also. So E is constant over this entire Gaussian surface. So I can take E outside of the integral. So we have integral over S. S is the Gaussian surface of ds only. And what would be that integral? It is just sum of all these small surface areas ds taken over the Gaussian surface. So that's why it is equal to just total surface area of the Gaussian surface. So this is equal to 4 pi r square. So we found the flux through the Gaussian surface is E multiplied by 4 pi r square. Now let's use the Gauss's law, and Gauss's law says that the flux is equal to charge enclosed divided by epsilon naught. So I can say, using Gauss's law, we have phi equal to charge enclosed divided by epsilon naught, and let's substitute this phi here. So we have E multiplied by 4 pi r square is charge enclosed divided by epsilon naught. And how much is the charge enclosed by this Gaussian surface? So it is the total charge. It's the total charge on this solid sphere. So which is Q. And epsilon naught as it is. Then I can take this 4 pi r square on the other side and rewrite this formula. So we get the magnitude of electric field as 1 over 4 pi r square into Q divided by epsilon naught, or we'll write it in suggestive form, is 1 over 4 pi epsilon naught into Q divided by r square. Alright, so this is the magnitude of electric field due to uniformly charged solid sphere. And now by looking at this formula, it is very clear that the electric field due to this solid sphere at outside point, a point which is outside the solid sphere, behaves just as if some positive charge is kept at the center of the sphere. And how much is magnitude of that positive charge? The magnitude of that positive charge is just equal to the total charge on the solid sphere. And what about the direction? So the direction of electric field is radial. So it is in radial direction. So this is electric field at a point outside of sphere. Now let's try to find the electric field inside the sphere. Okay, now we are going to find out the electric field due to a solid sphere at a point in interior region. So suppose this is solid sphere, its radius is this capital R, and this is point P at distance small r away from the center, where we want to find out the electric field. So let's again, we use Gauss's law, which tells us that phi, the flux through Gaussian surface, is equal to charge enclosed divided by epsilon naught. And we have already drawn the Gaussian surface in this case. So this is the Gaussian surface. Let's call it S. Now in this case, the charge enclosed is not total charge. It is just charge inside this smaller sphere, the Gaussian surface. And we need to calculate it. So how do we calculate the charge? So we considered that this charge in the solid sphere, it is uniformly distributed throughout the volume of the sphere. So there is this volume charge density which is constant, and we know that the volume charge density is charge divided by volume containing that charge. So we'll denote volume charge density by rho. Q is any charge in volume V. Then Q would be equal to, Q would be equal to rho multiplied by V. V is the volume, and therefore charge enclosed in this sphere, which is Q ENC, is equal to rho multiplied by the volume of this Gaussian sphere, the Gaussian surface. And that volume is just 4 by 3 pi multiplied by r cube. And r is the radius of the Gaussian surface. So we have calculated the charge enclosed. Rest of the things are same as that of previous case. So let's call this equation number 1. Now we know that phi is equal to integral of E bar dot ds bar over the Gaussian surface. So it is E ds multiplied by cos of theta. Now again we can argue in the same way as before that electric field at each and every point of the Gaussian surface is equal in magnitude and radial in direction. So the electric field at point P would be in this direction. So this is our E bar, and if we take this small surface ds surrounding the point P, then the ds bar is perpendicular to the plane of that surface. So ds bar and E bar, again they are in the same direction. So theta is 0. The angle between ds bar and E bar is 0. And therefore cos of theta is 1. So we have only E times ds. And again E is constant, so we can take it outside. So we just have this integral of ds over the Gaussian surface. And that integral is equal to just the surface area of the Gaussian surface. So I can say phi is equal to E multiplied by total surface area of Gaussian surface, which is 4 pi r square. Then let's use the Gauss's law. So using Gauss's law, what we can say is phi is equal to charge enclosed divided by epsilon naught, and we have found the charge enclosed as well as the flux. So let us substitute that in this equation, the Gauss's law. So phi is equal to E multiplied by 4 pi r square, and that is equal to charge enclosed, which is rho multiplied by 4 by 3 pi r cube, that's the charge enclosed, divided by epsilon naught. Now we have some cancellations here. 4 pi and this 4 pi gets cancelled out, r square gets cancelled out, and 1 r will be left there. So we have E equal to rho multiplied by r divided by 3 epsilon naught. Okay, so here we can say E is proportional to R. Alright, so this is the electric field at interior point. Now let us just write down the formula for electric field due to solid sphere. So the electric field due to solid sphere, E is equal to rho into R divided by 3 epsilon naught. This is for interior point, that is R less than capital R, and it is equal to 1 over 4 pi epsilon naught into Q divided by R square for R greater than capital R. So this is for exterior point. Now what if R small r is equal to capital R? So then we can just substitute R equal to capital R in one of these two formulae, and both will give the same answer, which is 1 over 4 pi epsilon naught into Q divided by R square. And the electric field is in radial direction. So we can try to plot this electric field versus R, and here we can say it is directly proportional to R. So as R increases, electric field also increases like this. At R equal to capital R, so it has this value, E equal to 1 over 4 pi epsilon naught into Q upon R square. So this is when R equal to capital R, and then it falls off as 1 by R square like this. So this is E equal to 1 over 4 pi epsilon naught into Q divided by R square. So more or less the graph between electric field and R will look like this. Okay, so we found the electric field due to solid sphere. Now let's move on to the hollow sphere. Let's try to find out its electric field. Alright, now let us try to find out the electric field due to a charged spherical shell or a hollow sphere. So suppose this is our charged spherical shell. This positive charge is uniformly distributed all over the surface of the shell, and we want to find out its electric field at this point at distance r away from the center. Capital R is radius of the shell. Now we need to apply the Gauss law, and again for that we need to draw a Gaussian surface, and it should be clear from the symmetries that Gaussian surface would be spherical, a concentric sphere whose center coincides to the center of the spherical shell. So this is Gaussian surface S. Now we know the Gauss law. The flux through any closed surface is equal to charge enclosed divided by epsilon naught, and flux is equal to integral of E bar dot ds bar. So we are applying the Gauss law over the Gaussian surface, which is S. Then again we can say that the electric field at this point P would be directed like this. Due to this spherical symmetry, it should be radially outwards. This is ds, a small surface surrounding this point P, and area vector for ds would be directed perpendicular to plane of ds. So again, this is equal to integral of E into ds multiplied by cos of theta, that is equal to charge enclosed divided by epsilon naught, and theta is 0 since E bar and ds bar, they are directed in the same direction. So theta is 0, cos of 0 is 1. So this is the integral of E into ds over the Gaussian surface. And again, since the magnitude of electric field would be constant over the entire Gaussian surface, we can take magnitude of electric field outside. So this is equal to E into integral of ds, and on right hand side we have charge enclosed divided by epsilon naught, and charge enclosed is just the total charge on spherical shell. So it is just Q divided by epsilon naught. Then this integral of ds over the Gaussian surface is just surface area of the Gaussian surface. So this integral is just 4 pi r square, that is equal to Q divided by epsilon naught, and therefore E is equal to, we can take 4 pi r square on the other side, so 1 over 4 pi epsilon naught into Q over r square, as simple as that. So this is the electric field due to positively charged spherical shell at a point which is in the exterior region of the shell. So this is in exterior region. Now what about a point in interior region? Again, let's consider that this is our spherical shell and this is the positive charge uniformly distributed all over the surface. Charge is Q. It has got radius R, and we want to find out its electric field at an interior point. So let's consider this point here in interior region, and let's draw a Gaussian surface passing through this point. Again, it will be the sphere. Like this. This distance is R. Now let's apply the Gauss law. So the Gauss law says flux is equal to charge enclosed divided by epsilon naught. Now how much is the charge enclosed by this Gaussian surface, this inner sphere? The answer is 0. So that's why flux phi passing through this Gaussian surface is equal to 0, and flux is integral of E into ds, that is 0. Now clearly ds is not 0, so what should be 0 there? The electric field. So I can say that E is equal to 0. Alright, so electric field in the interior region of a charged spherical shell is 0. So I can say E is equal to 0 if R is less than capital R, and it is equal to 1 over 4 pi epsilon naught into Q over R square when R is greater than capital R. So that's the electric field due to charged spherical shell. Now let us draw a graph, a plot between electric field and R, and the graph will look like this. Till R equal to capital R, the electric field is just 0. So it rises suddenly at this point, R equal to capital R, suppose up to this, and this should be equal to 1 over 4 pi epsilon naught into Q divided by R square, but at this point the small r is equal to capital R. So Q over R square is the electric field, and after that point the electric field falls off like this. So this is E equal to 1 over 4 pi epsilon naught multiplied by Q over R square. So for a point in exterior region, this spherical shell behaves as if a point charge is kept at the center, and in interior region the electric field is just 0. Now let's think, why would the electric field be 0 in the interior region? So suppose this is our spherical shell and it is uniformly charged. Suppose this is the charge. Now it's clear that the electric field at the center would be 0, and it's because, suppose this is center, if you consider some small region on this side of the center, let's say ds, and the region diametrically opposite to it, again of same surface area, then this is positively charged, that is positively charged, and therefore the electric field due to both of them will be equal and opposite. So the electric field at center would be 0. So the electric field at center is 0, but it's not clear why should the electric field be 0 at any other point. Let's say for this point. So why should the electric field at point P be 0? So let's try to think. So let's consider surfaces like this surface, and diametrically opposite surface. Now they are no longer equal, so again charge on them is not same, charge is different. So we can say this is dq1 and that's dq2, But this spherical shell is uniformly charged, so we can define a quantity called surface charge density. Sigma, which is charge divided by area, surface area. So let's say Q divided by ds. So charge dq1, here we can say Q is equal to sigma times ds. Then dq1 should be equal to sigma multiplied by ds1, and therefore dq2 should be equal to sigma times ds2. Okay, then what is electric field due to this surface? Let's say ds1 at this point. So d1 is equal to 1 over 4 pi epsilon naught, we can say it's constant, times dq1 divided by r1 square. This distance is r1, or this distance is again same. So electric field due to this surface at this point is equal to 1 over 4 pi epsilon naught into charge on this surface divided by r1 square, and electric field due to that surface, which will be directed opposite to this electric field, dE2 is k into dq2 over r2 square. So again we can say this is equal to k into dq1 is sigma times ds1 over r1 square, and this should be equal to k into sigma times ds2 over r2 square. Now if the electric field due to this surface and that surface at this point is equal in magnitude, then the total electric field will be 0, because the electric field due to this surface and that surface, they are opposite in direction. So question is whether dE1 is equal to dE2. That means whether this part, since k and sigma it is common in both, so ds1 over r1 square, is it equal to ds2 over r2 square? If it's equal, then the net electric field at point P is equal to 0. So the question is whether ds1 divided by r1 square is equal to ds2 divided by r2 square, and indeed it is same. It's because ds1 divided by r1 square is the solid angle subtended by this surface ds1 at point P, and ds2 by r2 square is the solid angle subtended by this surface ds2 at point P. And solid angle is just the cone subtended, it's the 3D angle, and you can imagine that whatever is the cone subtended, the solid angle subtended by ds2, the same would be the solid angle subtended by ds1. They are vertically opposite solid angles. So that's why we can say that the solid angles are same. ds1 by r1 square is equal to ds2 by r2 square, and that's why the dE1 is equal to dE2. And hence, since dE1 and dE2 they are directed opposite to each other, the net electric field at P is also 0. So the electric field in the interior region of uniformly charged spherical shell would be equal to 0. Okay, so now we know how to find out the electric field using Gauss's law. We have seen quite a few examples. Next time we will see some problems on the electric charges and fields. Thanks for watching.